In this video, we're going to take the Biot-Savart law, written one way like this, and derive a couple of main results about the magnetic field produced by some common current distributions. So there will be two main examples that we're going to go over. What's the magnetic field due to an infinitely long wire? And the second one will be what's the magnetic field due to a loop of current? So just like a circle of current that's going around itself. The first example, the infinitely long wire, we're actually going to have another derivation in the next video when we talk about Ampere's law. So if you think back to electrostatics, we did two different proofs of like what's the electric field due to an infinitely long line of charge. So one was by integrating it piece by piece, and the other one was doing it by Gauss's law. So we'll have something similar with magnetism. We can integrate piece by piece, which is the focus of this video, or we can use symmetry along with a more conceptual, well, seemingly conceptual, but actually there's a quantitative statement associated with Ampere's law to answer that question in a more simple way. All right, so this is one way of writing Biot-Savart law on the bottom. You can write it differentially like this. So there's some constant, mu naught over 4 pi is just a constant divided by another constant. And here's the real piece. So you have a little piece of current. So current I in a section of wire of length ds. And the ds is a vector. So the length is the magnitude of ds, and the vector is pointing in the direction where the current is flowing, conventional current. And we cross this with r hat, divided by r squared. So r is from the current, from the piece of current, which is, infinitesimal in size, so very, very small. So it's at a well-defined point in space. It's just really tiny. You take that location. So really this delta s right here, like you can shrink it down to infinitely small. So, here's the IDL piece. R hat is pointing from the source, which is this piece of current, to the point where we want to calculate the magnetic field. So this is r vector. So r hat points in that direction. It's a unit vector pointing in that direction. And r is the magnitude of that vector, or in other words, the distance from the piece of current to the point of interest. So you'll notice that there's a cross product in this formula for the Biot-Savart. And notice, this picture is nice for seeing what the direction of that magnetic field contribution would be. So you have the direction of the current, just going one direction, and then the r hat vector is in another direction. Now those two vectors, if they're not parallel or anti-parallel, define a plane, and the magnetic field contribution is going to be perpendicular to that plane. So we have this direction, and then we could have the other direction here, but the direction is determined by the right-hand rule. So again, take your right hand, point your fingers in the direction of IDS. So in this case, you would start with this one, and then curl your fingers towards the direction of the r hat. So towards this one, and you'd be left with, this is the direction of the magnetic field contribution. So we're going to take this formula and integrate in order to find the total magnetic field from all of the pieces of current that comprise the current distribution. So the first example is done in 29.3. So you could either read this or I'll go over it again pretty quickly in this video. So you have an infinitely long wire. And let's say we want to, and the goal is to calculate the magnetic field here, which is a distance r away from the wire. So the way that we're going to go about this is we look at a little piece of current. So this is saying focus on this piece of the wire. So it has width dx, and I dx is the piece of current that we're looking at. It's pointing to the right. So I dx, and then to the right. And then this will be our R value. I guess your book used, so what your book did is, so because in the Biot-Savart law, R is this distance right here. It's like, well, what do you want to call R? Is it this or this? So the final result that we're going to have is written in terms of this R. So what your book does is it replaces this with Y for a moment, just to do the calculation. And at the very end, they replace Y back with R. So you'll see this is what they do right here. They have an answer in terms of Y, and then they rewrite it in terms of R. So they redefine what they mean by R. All right, so So let's see what the Biot-Savart law says for this. So this piece of current has a contribution to the magnetic field. So we got to be a little careful with signs because this is really a vector. So let me just point out that the IDL piece is always going to be pointing to the right, no matter what piece of the wire we're looking at. And when we cross that with R hat, we're always going to get contributions that point straight out of the page. So we're going to call this is going to be the Z direction. And so all of the contributions are going to point in the positive Z direction. All right, so notice when you take look at any piece of the wire, IDL points to the right. And if you curl your fingers towards the R hat direction, you get your thumb pointing out of the page in the direction, in the plus Z direction. Okay, so with that knowledge, so here we can write mu naught over 4 pi I dx cross R hat. So I'll write this to the side and then delete it. So you have I ds, let's write dx vector cross R hat. So we already know that this points out of the page. If we were going to look at the magnitude of this thing, well, it's the magnitude of the first piece, I dx. The magnitude of the second piece is 1. So like magnitude of R hat is just 1 by definition because it's a unit vector. But then we need to take sine of the angle between them. So here in this picture, we need to take I dx sine of theta, where theta is as labeled in the diagram. And then this is divided by R squared. Okay, where it's this R right here. So that's what the Biot-Savart law is telling us for the contribution to the magnetic field due to this piece of current that's over here. Right, so the closer theta is to 90 degrees, the bigger the contribution is. So in other words, for a fixed width, the piece right here is going to have a bigger contribution than the piece right here, which makes sense. Okay, so let's keep this going. So so the total magnetic field is going to be the integral of this thing, I dx over, I'm going to write everything in terms of x because we have the dx already written and we can write the other things in terms of dx. So the 1 over R squared is 1 over x squared plus y squared. Right, this is just the Pythagorean theorem. And then the sine theta, maybe I'll write that separately. The sine theta is opposite over hypotenuse for this right triangle. So it looks like this is y over r, or y over square root of x squared plus y squared. So in other words, we can replace sine theta with y over the square root of x squared plus y squared, and that turns this, instead of this to the first power, now it's to the 3/2 power. Because it was to the first power, and then we have another that to the 1/2 power, and when you add those two exponents together, you get this to the 3/2 power. So what we get here is bz is mu naught over 4 pi. We can take out the I and the y, those are constants. And really, we're just trying to integrate from x equals minus infinity to infinity, dx divided by x squared plus y squared to the 3/2. So this becomes a calculus problem. You could solve it in various ways. But this winds up being equal to mu naught I over 2 pi y. And remember, at the very end, we're going to replace y with r and say, well, we're a distance r from the wire, and the final result is mu naught I over 2 pi r. Yeah, so that's one of the main results, and we're going to have another way of deriving this with Ampere's law in the next video. The other main problem that we want to be able to solve here is the magnetic field due to a current loop. So suppose we have a circle of radius r, and it has a current I that's going around either clockwise or counterclockwise through this loop. Now, if we look at any piece of current here, let's see, let's get this out of the way. So this is radius r. I'll just write down here, radius r. And let's look at a piece of current right here. So this piece of current, it looks like it's going down at that point. So we'll call this IDS, so DS for arc length. And it's pointing tangent to the circle in the direction of I. If you look at IDS cross R hat, so R is going to be pointing straight towards the center of the circle. So this would be the R hat direction. If you look at IDS cross R hat, so one thing to notice is that no matter what piece you're looking at on this loop, IDS cross R hat is going to be perpendicular to the plane of the screen. So it's actually, these two are always 90 degrees. And no matter what, for this current direction, for this problem, this is going to point out of the page. Right? So this points out of the page, the magnetic field at the center. So this is the magnetic field at the center of the loop. Sorry. Probably should have said that from the very beginning. So we want to know the magnetic field here due to all of these things. So the magnetic field here is going to be out of the page. So again, we can set up this formula, BZ, we'll call Z out of the page. So the differential piece is mu naught over 4 pi. IDS cross R hats. So again, we're going to separate out the magnitude and the direction. So we already know the directions out of the page. So we can just write IDS. And the sign of the angle between the current element and the R hat is 90 degrees. So that sign theta is always sine of 90 degrees. So we don't need to include that piece. Divide by, and then this is pretty easy as well. This is just, it's always going to be that constant radius R squared. So the total magnetic field at the center is mu naught over 4 pi. And then integrating this thing over the circle, the entire circle, IDS over R squared. And we can actually take out the I over R squared. So this is mu naught I over 4 pi R squared. And then we're integrating the arc length of the circle, so ds, over the whole circle. So that's just the circumference of the circle. So that gives a factor of 2 pi r. So this right here is 2 pi r. So 2 pi r divided by 4 pi r squared gives it 1 over 2r. So it's mu naught I over 2r. So for this particular problem, for this current direction, the magnetic field points out of the page. If the current were instead going in the clockwise direction, then this magnetic field would be into the screen rather than out of the screen, but it would have that magnitude. So notice how also if we had like a quarter of a circle, so any arc section, arc length that is an arc of a circle would have this result, but times whatever fraction of a circle you have. So like if you had a quarter of a circle, it would be a quarter of this value. If you had a half a circle, it would be half of this value. So you could generalize this problem and say, well, it's this answer times whatever angle you subtend over 2 pi radians. Right? So if you have a whole circle, then phi is 2 pi, and then bam. If you have multiple loops, then you could also introduce a factor of n right here for the number of loops of current, because you'd be integrating over an angle that's more than 2 pi. And I think actually, so your book does the second example here, the magnetic field of the current loop. And I think they keep, the factor of n in there. So they say that we definitely have an integer number of whole loops, of whole circles. So they don't have this angle thing in there, but they do have the factor of n for n number of turns of loop. Okay, so if you want a really strong magnetic field and you have some wire, you could maybe coil it. And the more coils you have, the stronger the magnetic field. And also the stronger or the smaller the radius, the bigger the magnetic field. So you probably want a bunch of small loops as much as you can. This idea of a current loop, oh, by the way, your book does this in more generality. So they talk about this as a function of z along the symmetry axis as well. So we took z equals 0 when we did this, but your book does this for the non-z equals 0 case. So you just have to be you have to take just the component that survives, which is the component of the magnetic field along the z-axis, but it's pretty similar calculation. A magnetic dipole is exactly this thing that we just looked at. This is a current loop. So this is sort of the smallest thing that produces a magnetic field is a current loop. Remember, we can't, so later we're going to talk about the fact that like permanent magnets are just a bunch of current loops. Even at the microscopic level, like electrons are kind of just going around in circles. Or they in themselves act like little current loops because maybe they're spinning. But whenever you have charge going around in a circle like this, it creates a magnetic field. That's the point. Charge moving around in a circle creates a magnetic field, and it's a magnetic dipole moment. So it acts like a bar magnet. This loop of current right here, so shown in this picture and then viewed on the side like this, it acts exactly the same as a magnet where the north end and the south end are like this. So notice how the direction of the magnetic field lines come from the north side, from the North Pole, and then end on the South Pole of the magnet. The current loop acts exactly the same as a permanent magnet. That's sort of the surprising thing. So your book motivates, and this is what they're saying here, your book motivates a definition of something called the magnetic dipole moment, mu. So rather than talking about a loop of wire with some radius or some area, so you had the area of this thing was A, so pi r squared for a circle. If you have area A and current I, we define this thing called the magnetic dipole moment, mu, which is a vector. So this is going to be the magnetic analog of P. Remember we had the electric dipole moment, P was Q times the distance separating the two charges. So we define this thing P, and that told us everything about like how this thing acts. And like you put an electric field on it, you turn an electric field on, the P wants to line up with E. It's the same thing here with the magnetic field. Mu is going to want to line up with B. We're going to talk about that in a couple of videos as well. So we can sum up how this current loop acts by defining this thing called the magnetic dipole moment. It's the area of the loop times the current in the loop. And then some books would write also the number of loops of turn as well, but it looks like your book is just considering a single loop. And then the direction is determined by the right-hand rule. So the direction will be perpendicular to the loop. So here we have, this loop has the plane of the screen. And the direction of this thing is the same as the direction of the magnetic field produced by the magnetic dipole moment at the center. So like this loop is producing a magnetic field at the center that points out of the screen. So for this example, mu points out of the screen. So the direction is going to be perpendicular to the plane. Direction is perpendicular to the plane of the current loop in a direction consistent with the right-hand rule. So another way of doing this is to take your right hand and curl your fingers around the direction of the current, and your thumb is pointing in the direction of the magnetic moment. So that's another way to figure this thing out too. The magnetic field produced by a dipole on the axis takes on a pretty simple form in terms of the magnetic dipole moment. So we can't isolate a north pole or a south pole by itself. So this is kind of the smallest, the smallest unit of, or the smallest thing containing a magnetic field that you can talk about. You can't talk about a north pole of a certain magnetic charge because we don't see those in nature, but we can talk about magnetic dipoles. All right, so some of your problems are just going to be making sure you're familiar with these two results. So here's an example where it looks like we're talking about half infinite wires. So we have a wire that comes from infinitely far away. So and then all of a sudden it makes a right turn and then starts going down off to infinity. And we want to know the magnetic field at point P, indicated in red. So you just have to recognize in a problem like this, you have to recognize, oh, we've seen this problem a lot. It's the magnetic field of an infinite wire. And here it's actually a half infinite wire, right? If you had an infinite wire, you would have to sum up contributions from both sides of the wire. For a half infinite wire, you actually have, it's actually half of the result. So if you go back to our derivation over here on the right, if you go back to our derivation, if we integrated from minus infinity to 0, you'll notice that we're integrating an even function. So if an even function has the same value whether x is positive or negative. So it's twice the value of just integrating from 0 to infinity or from negative infinity to 0. So that's one fact that we're going to have here. Another fact is that notice how the pieces here have IDL pointing down, or IDS pointing down, and the R hat is pointing up. Like if we were looking at this bottom wire, and we thought about what the contribution of any piece of current is to the magnetic field at point P, it's 0, because we have IDS pointing down and R hat pointing up. And if you take the cross product of those two pieces, you always get exactly 0. So in other words, if we split this up into contributions 1 and 2, so the total magnetic field at point P is the magnetic field contribution due to the first part of the wire plus the magnetic field contribution due to the second part of the wire. So this one's going to be 0 because you're summing up a bunch of contributions 0. And this one, B1, is going to be 1/2 the magnetic field due to an infinitely long wire, infinite wire. And we saw before that this was mu naught I over 2 pi r. And here we're labeling the distance from the wire d, right? If this was an infinitely long wire, that distance is d. So it looks like this, and we use the right-hand rule. Take your right hand, wrap it around the infinitely long wire with your thumb pointing in the direction of the current. It looks like your fingers are pointing out of the board right here. So this is out of the screen. So overall, our magnetic field is, if we can just multiply through by the 1/2, mu naught I over 4 pi d out of screen. That'll be our result. Okay, so yeah, any sort of time you're given a circle, a fraction of a circle, an infinite wire, a half an infinite wire, you should be able to combine all of those pieces to get the overall magnetic field from any combination of those things.